Hi, this is Mrs. Villette, and in this video I'm going to show you how to solve equations higher than second degree. I should note that we're pretty limited to nice equations, so that means that they need to be easily factorable either by factoring out a GCF or difference of cubes or factoring by grouping. So these are the types of problems you will see in your homework or on a quiz. This first example, we have a trinomial cubic on one side and another trinomial cubic on the other side. Now, in order to start solving this, our first thing to do is to get everything to one side. So all I've done in this first step is subtracted the right-hand side over to the left-hand side. So that's why I have a negative x cubed, a positive x squared, and a negative 9x. And you can probably guess that the next step is going to be to combine like terms. So that's what I've done here. I've combined the like terms. So 2x cubed minus x cubed gives me just x cubed. 3x squared plus x squared is 4x squared. And then I put the negative 9x and the negative 36. When you have a 4-term polynomial, you should try to factor by grouping. So this first group has a GCF of x squared, and this second group has a GCF of 9. Actually negative 9, now that I'm looking at it. So I will factor out by grouping. Factoring by grouping, I've factored an x squared out of the first group and a negative 9 out of the second group. Then I have a common binomial factor of x plus 4, and then an x squared subtract 9. I need to factor this x squared subtract 9 more, so that's what I do next. That's a difference of squares. It factors into x minus 3x plus 3. Now I still have, notice, this equals 0 this whole time. The whole idea behind getting everything to one side and 0 on the other is so I can use the zero product principle. And that's what I do at the end. Notice this was just a solving problem. It wasn't to find x-intercepts or look at the graphs or anything. So I just solve using the zero product principle. And in this case, I just did it by inspection. Negative 4 plus 4 will give me 0. 3 minus 3 will give me 0. Negative 3 minus 3 will give me 0. So I have my 3 zeros, and you can list them in any order that you want. So if you see an equation in your 3.5 homework, just go ahead and get everything to one side, factor appropriately, in this case by grouping, and then apply the zero product principle. Okay, so there are two options for solving inequalities, and both of them require that you get everything to one side. The first option is factor and use a sign chart. The second option is to factor and use what you know about the graph. So I have these two examples, and I'm going to show you both options. Okay, so our first example, 25 minus x squared, is less than 0. Getting everything to one side is already done, so I just need to factor. And I'm going to factor this as a difference of squares, so 5 minus x, 5 plus x. That gives me zeros at 5 and negative 5. So this sort of shows you the options, but walking you through the sign chart, I would first mark off my zeros at negative 5 and 5. Then I would choose test points between those and on either side of them. So I chose test points of negative 6, 0, and 10. And then I'm going to actually plug each of those test points into, it actually should be the original inequality now that I think about it. That probably actually would have been easier, in fact. But I plugged them into the factored form. So plugging negative 6 into the factored form, I got negative 11 is less than 0, which is true. So I wrote true up there. Plugging in 0, I got 25 is less than 0 is false. And then plugging in 10, really it can be any test point, I got true. That means my inequality is true for everything to the left of that test point and everything, not the test point, the boundary, and everything to the right. So our answer that we end up writing is negative infinity to negative 5 union 5 to infinity. Okay, our option 2 would basically involve the same thing. Moving everything over to one side, I rewrote the function in standard form so that I could see it had a y-intercept at 25, a negative leading coefficient, and then I went ahead and factored out a negative and factored the difference of squares, which gives me a graph that looks like this. Y-intercept at positive 25, flipped over, and then x-intercepts at 5 and negative 5. I want to know when this function is less than 0. So I shade the part that's less than 0, and then I simply write the interval notation that corresponds to that. Our next example is very similar, except everything isn't moved to one side. So I have x cubed is less than or equal to 9x. My first step is going to move everything to the left-hand side and 0 on the right. So you can see I've done that. I've subtracted 9x. Then I'm going to factor. First, I factor an x out, and I get a difference of squares, which I then factor further. So I have x times x minus 3 times x plus 3 is less than or equal to 0. So I'm going to make my number line, or my sign chart, with 0, 3, and negative 3 marked off. So I have those kind of in maroon there. Then I'm going to choose these sample points. So I chose negative 4, negative 1, 1, and 4. I'm going to plug each of those sample points into the original inequality. When I plug into the original inequality, I'm plugging in up here before I moved things over, and I get negative 64 is less than negative 36 when I plug in negative 4, so I write true. And then I just go through for each one. Negative 1 is less than or equal to negative 9, false. 1 is less than or equal to 9, true. 64 is less than or equal to 36, false. Then my solution set will actually be the true sections, and we're going to include the endpoints because of the less than or equal to. So between negative infinity and negative 3, and then between 0 and 3. And that's what I write down here in my interval notation. Option 2 is basically the same idea. We are going to move everything to one side and factor. Then I'm looking for when I want that function to be less than or equal to 0. I've made the graph with the x-intercepts at 0, 3, negative 3. My leading coefficient is positive, and it's an x cubed, so I know what that means for the long run behavior. The multiplicities are 1, so it crosses through each x-intercept. And it's going to be negative here, so negative infinity to negative 3, and then 0 to 3.